So Section 4.4 deals with a couple of topics where logarithms, exponentials, and the derivatives of them are playing into use. Um, it certainly is not as big of an section as what a typical calculus course would expect you to do with logarithmic differentiation, although some of that is being shown here. Um, so the first thing we talk about is a relative versus absolute rate of change. So when we found derivatives for many circumstances, particularly where time was involved, we were typically finding what was known as an absolute rate of change. The problem is if I compare absolute rates of change, um, if I'm trying to find the effect of inflation is on several different products, like here, for instance, automobiles versus shoes. Shoes are increasing at a rate of $3 per year, say, and automobiles are increasing at a rate of $300 per year. That makes it seem like, that automobiles are increasing 100 times faster or as fast as shoe prices. If you're comparing absolutes, yes, but is that really the effect? I mean, because the thing you're not taking into consideration at that point is that there is already a drastic difference in cost between shoes and automobiles. So the reason why we have to sometimes use relative, which is what we compare percentages of change, um, to compare situations like this, the units and other things like differences in costs that already exist don't play as big of a role. You may find out that shoes are increasing much faster than automobiles, even though it's a $3 raise versus an automobile's $300 raise. So we calculate what's known as a relative rate of change by doing the derivative of a function, usually with respect to t, divided by a function, which is also usually with respect to t. So again, the derivative itself is the absolute rate of change, whereas the derivative divided by the original function is a function that gives me the relative rate of change. Um, they go into an example here, that basically, it could be easier to see what the actual, change is. If I say that the gross domestic product is increasing at an absolute rate of $400 billion per year, that makes it sound like it's drastically increasing. Because I mean that's a big number. None of us would ever see that much money, so it's an unimaginable amount of money for us. However, if you're comparing it to the amounts of money that government and infrastructure and things deal with, it's a 3% raise. A 3% raise, if you got a 3% raise, it's helpful, but it's not life changing. Um, so sometimes the relative rate of change is a better description of what's actually going on, and it's another idea of how numbers can be used to manipulate things. I mean, if someone wants to say this is bad, they'll present a $400 billion per year increase, whereas if they're trying to show it's not as bad of a thing, they'll say, well, it's a 3% increase. So so relative rates of change. I mean, we can actually also calculate this a little bit easier, because sometimes the functions that you have to deal with um, are a little tougher if you do the derivative of it and then divide it by the function itself. But if you take the natural log of the function and then do the derivative of that, that would give you the relative rate of change. And that's because, if you remember, that's why I still felt it was important to show the formula for it, even though it's just a result of the chain rule. That if I do a natural log of a function of x and I want to do a derivative of that, that's the same thing as doing f prime of x over f of x. So, but again, that was always the result of the chain rule, so that wasn't a formula we had to remember, but it's a good idea to look at that and know that, okay, that also represents the relative rate of change, and therefore we can do it that way as well. They go into why they use t. It's usually a result of time. That's something that's not unfamiliar to us. So So an example here, if the gross domestic product T years from now is predicted to be G of T equals 8.2 times E to the square root T trillion dollars, find the relative rate of change 25 years from now. So they're going to show two solutions here. They're going to use the derivative of the natural log formula, and they're going to use the f prime of x over f of x formula. Kind of show you it gets the same thing. So it doesn't matter which one you choose to use whichever one's more comfortable. So here, the first one they're going to do is they're going to do the derivative of the natural log of f of t. So they're going to do the natural log of g of t, which is the natural log of 8.2 times e to the square root t. One of the things I want you to keep in mind is that as we go through this, I'm guessing that they had some issues with the way it was scripting. You know, this is always going to be the natural log of 8.2 times e square root t. Even right here, it starts looking like it's an exponent. It's really not supposed to be. It's supposed to be written, you know, as 8.2 times e square root of t. And I don't want you to think that somehow this is becoming an exponent in the long run, because that could certainly lead to some confusion. So, because what we do next is, well, since that is a product, then I could turn that into the natural log of 8.2. This is just a constant at this point. I don't actually have to figure out what it is, but it's a constant. I haven't taken a derivative yet. That's why I'm making it a point to note that's a constant. So when I eventually do take the derivative, that's going to become 0. This, of course, is the natural log of e square root t. There's going to be some cancellation between these guys, because the natural log is log base e. E to the square root t means an exponential base t. So when I simplify even further, I get that this is equal to the natural log of 8.2 plus the square root of t. So that's what the natural log of g of t is. Now I'm going to do the derivative. Well, I'm going to turn it to the 1/2 power next. And now I'm going to do the derivative of that, because this is the derivative of, again, this is g of t. The natural log of it. So I do a derivative of this. I get 0 plus 1/2 t to the negative 1/2. Because the 0 kind of just goes away. And then at this point, you know, I can calculate what's going to happen when t equals 25. And I get essentially that this is a rate of change of 0.10. Now recognize that, you know, this is a decimal like this, but this is also a percentage that we're calculating here, because anytime you calculate a relative rate of change, it is a percentage. So based off of these results, the gross domestic product will be increasing at the relative rate of 0.10 or 10% per year. Now let's use the other formula, f prime of t over f of t. So again, we start with g of t, which is just, and again, they changed the square root into a t to the 1/2 power. For some reason, this one seems to be sitting better as far as their graphics go, which is nice. And now I'm going to do a derivative of that. So usually if I have e involved, I'm going to be rewriting the statement again. So, you know, 8.2 times e to the t to the 1/2 power has taken care of the derivative of the e to the t 1/2 power. The 8.2 is a constant multiple. It just kind of go along for a ride. This part here is the derivative of the exponent. So we have to do the derivative of this part according to the chain rule. So I get 1/2 t to the negative 1/2 power. Excuse me. So if I now do the proportion of g prime of t over g of t, I can see how it sets up. I can also see how these are going to cancel, leaving me with 1/2 t to the negative 1/2 power, which is the same formula we had when we applied the natural log and then differentiated. So from here on out, everything else is the same, and it still indicates a 10% growth in the gross national product. So both ways will do. Sometimes it depends on what the functions are that are going to determine if one's a little easier algebra-wise than the other. But it's something that only you can get a hold of with some level of experience. So now it's your turn. Look at this question here, and I'll give you a moment to work on it. Of course, the video will pause. During 2012 and 2013, the price of 3D Systems stock has was growing rapidly and was given approximately by this expression 15e to the 0.805x power, where x is the number of years since 2011. They want you to find the relative growth rate of the stock during that period in 3D systems manufacturers, 3D printers. So take a moment, make the necessary calculations, and we'll talk about what the relative growth rate of this stock was during that time period. Okay, so you've given it your try now. So let's have a look at this. Basically, the price of the stock is given by the function that. So I'm going to use the relative growth rate. I'm going to calculate the relative growth rate using logarithm, the natural log, the derivative of natural log, because of the fact that I already see an e in here, and I know that e's cancel pretty easily with natural logs. So from an algebra standpoint, it seems like to me it'd be a little easier that way. So I'm going to first decide what the natural log of p of x is. So I'm going to have the natural log of all of this. And according to the product property, that's going to be the natural log of 15 plus the natural log of e to the 0.805x power, which of course just becomes the natural log of 15 plus 0.805x. So that's my that's the logarithm of this price function. Now I'm going to do the derivative of the natural log of the price function here to get its relative rate of change. So I'm going to do the derivative of this. Now again, natural log 15 is just a constant, so when I do its derivative, it becomes nothing. The derivative of 0.805x, it's just basically I have a constant multiple of 0.805. The derivative of x is just 1, so I end up with 0.805. And that's what the answer is, 0.805. So that's the relative growth rate. So, and it doesn't, you can see here, I have no mention of x. So, I don't have to plug in any number to represent, the time period here. During this entire time period, it was a pretty constant relative growth rate. So I would say that in this case here, the stock was increasing by a rate of 80.5% per year. So that's the first question. Now, the other thing we take a look at in the 404 and spend a lot of time is a concept known as elasticity of demand. Basically, I mean, a lot of the business information that's coming into this, I mean, it's kind of segmented, and I'm certainly no business expert myself. I'm more of a math guy. So, the basics about how this works is, I mean, obviously, if I have prices that are too high, the demand's going to be low. Okay. Well, if I have a huge supply at times, sometimes I have to lower the price. And, and sometimes doing that'll increase the demand enough to use up enough of your supply that you're going to make money. You're going to earn a lot of revenue. But sometimes, like if you get into, especially like, like what they're saying, farmers or ranchers, where when you actually have, different seasons where, what you're able to grow and produce is different based off of, various things. If you have a bumper crop, that can actually in the end cause you to lose money. And you actually have less revenue coming in as a result, because if you have such a high supply, the demand I mean, you may lower the prices so the demand comes up, but the demand may not increase enough as the prices get lowered to, compensate you enough to earn enough revenue. And that's what the full process of elasticity is. Um, they go into some specifics here, but I think it's kind of like basically here. Elasticity is basically a percent. It's a ratio of the percentage change in demand over the percent change in price. So and they give you how it's calculated, and we actually use a different function for this, but essentially behind it is in a situation where I get this ratio to be a value that's more than 1, then we say that the demand is elastic, and we'll talk about what that means momentarily. If E is less than 1, then it is inelastic, and if the demand is unit elastic, if E happens to equal 1, and we'll talk about what these three things all mean. But essentially, elasticity is basically responsiveness to the change. So price changes being I mean, if I have demand, elastic demand, that means that a price change is going to cause a very noticeable change, good or bad. And typically, the way it usually works is like, since decreasing price usually increases demand, then obviously if it's elastic, then I'm going to have a noticeable increase in demand, and it's going to make a noticeable change in my revenue. Inelastic means unresponsive. So basically what that means, if I lower prices, the demand's going to maybe go up, but not, anything noticeable that's going to create more revenue coming in to make up for the decrease in price. Um, so basically, for inelastic demand, a price cut will bring only a slight increase in demand, so total revenue will still tend to fall. And here they go through a specific example with elasticity values here. Um, so as we do this calculation of elasticity of demand, um, the demand function is going to be represented by the quantity that's demanded is going to be given to us by a function d of p, where p stands for the price. Um, if I have that demand function calculated, the elasticity of demand is calculated by doing negative p times d prime of p over d of p. You notice you have that d prime p over d of p. So basically it's negative p times the relative growth rate of demand. So it's based off of a relative growth rate rather than an absolute growth rate. Um, and that's why it's done that way, because it doesn't necessarily relate to, it doesn't really, it's relative. It's not based off of the units of the demand function. So because sometimes the units that are being used can certainly throw off calculations. So in order to calculate elasticity of demand, let's see what we could do with this, and see if we could signify it as being elastic or inelastic. So a bus line estimates the demand function of its daily commuter tickets to be given by the function d of p equals 81 minus p squared, which gives us a value, which gives us a number of in numbers of tickets. So this is what represents the demand of, in thousands, where p is the price in dollars between $0 and $9. And sometimes they'll do that because it may follow one function for one, interval of prices, and then go to a different function altogether for another interval of prices. So find the elasticity of demand when the price is $3 and $6. Well, first we have to find a function to plug this into. We have to find the elasticity of demand function. So E of P is given to us by this formula, where I take negative P times the relative growth rate of the demand function. Since D of P equals 81 minus P squared, they chose us to keep the D prime of P over D of P instead of doing any logarithm stuff. If I had stuff with E's involved, I might, go with that route, instead. But the derivative of, 81 minus P squared is negative 2P. So I end up with a function, when it's simplified, of being 2p squared over 81 minus p squared. So this is the function that's going to tell us, the elasticity of demand. So now I have to put the actual price points in. So for $3, I plug that in and I get 1/4. That means that at this price point, the elasticity of demand tells me that it's inelastic at a price of $3, which means that a small price change up or down from this level will cause only a slight change in demand. More precisely, elasticity of 1/4 means that 1% price change will cause only about a 1/4% change in demand. Whereas if it was at a price of $6, when I calculate, I get 1.6, which means here the demand is elastic, which means that a small change in price up or down from this level will cause a relatively large change in demand. So basically, in this case, if I lower the price a little bit here, I'm going to have a noticeable change in the amount of demand, and that's going to make me earn more money. So basically, sometimes prices are changed in a situation to go from a circumstance where it's inelastic to elastic, so that I can, if I could cause a price change, and to maximize the revenue, that's how decisions are made, whether I should lower a price or raise a price. So before we get into that, though, let's have you have a try at calculating an elasticity of demand and rating it as elastic, inelastic, or unit elastic. So here's your problem. You're given D of P, you're to find the elasticity of demand, and you're to identify it. You're also given a price, point, and you're asked to determine if it's elastic, inelastic, or unit elastic at the given price P. So take a moment and answer that question. So here we are. So here we go with this. I had to calculate, first of all, a function for E of P. What I see here is I see a square root function here. I don't see any benefit of just using a natural log of any way with this. So I am going to, as I said, I could use a formula that says that E of P is negative P times D prime of P over D of P. But I also could say that's the same thing as d dx of the natural log of, or take that back. Yeah. Sorry, I put that a little too soon. I could also say it's essentially negative P times the derivative, in this case it's going to be per P, of the natural log of D of P. As I said, either way is able to be done. A lot of the circumstances are going to give you kind of fit this formula best, so a natural log is not necessarily going to help you considerably with it. So for this one here, D of P equals 100 minus 2p to the 1/2 power. I'm also going to calculate d prime of p at this point, which equals 1/2 of 100 minus 2p to the negative 1/2 times the derivative of 100 minus 2p is negative 2. So d prime of p, when simplified, is going to equal negative 100 minus 2p to the negative 1/2, or negative 1 over the square root of 100 minus 2p. So now when I actually calculate E of P, I'm going to have negative P times this. So I'm going to have negative P over the square root of 100 minus 2p all over the square root of 100 minus 2p. Oh, and that should be a positive p now because it was negative p times negative 1. So that should be a positive p. If I'm taking something and dividing it by, a quotient divided by something else, I just multiply the denominators together. So this ends up being p over the square root of 100 minus 2p times itself, which means I'm essentially squaring a square root. So here, that just becomes 100 minus 2p. So that's the function that gives us the elasticity of demand. So that answers part A. Part B, I want to evaluate that when it's $20. I'm guessing it's dollars. They don't say what the price is. That could be $20, 20 cents. We don't know. So I'm going to have 20 over 100 minus 2 times 20, which equals 20 over 60, which is 1/3. And that's less than 1. So I would say that demand is inelastic. Now, knowing if it's elastic or inelastic or what, what does that tell us? What does that tell us to do as far as prices go? So, how do I increase my revenue? So we're going to talk about that briefly. And they kind of recap some of the information here from previous examples, but the main deciding factor that we're going to be using for this is this. Essentially, if the demand is elastic, then prices should be lowered because that's going to increase the demand enough and that's going to increase your revenue. If at a certain price point your demand is inelastic, then you should increase the prices, because at that point you're going to be increasing the income from the little demand you have. And plus, since you are changing, if it's inelastic, any change you make is not going to change demand noticeably. So raising the price is not going to necessarily cause your demand to fluctuate by any meaningful amount, which means you will make more money because basically the same number of people are going to be buying it at just a higher price. So, the other thing we want to keep in mind is the borderline case of unit elasticity when E equals 1 is where revenue cannot be raised. That means you're earning the highest possible revenue at that point. So one way that we sometimes will study and look at, depending on the information you got, if you have a revenue function in terms of number of products being made or things like that, then we're going to use our standard methods of finding a maximum. However, if you're given a price, you're really not told like how many are being made. You don't worry about warehouse and storage prices and all the things we talked about prior. One of the ways to maximize revenue, not necessarily profit, but revenue, is to make sure that you have an elasticity. Your elasticity calculation becomes 1. So, so we can use this fact as a new method for maximizing, but instead we will stick with our earlier and easier method of maximizing functions by finding critical numbers. The thing is, though, they do give you some circumstances where, if you're told that, you have a function, the information they give you, it's actually easier to determine if your elasticity value is 1. So don't take this as being like, a statement that you're not going to have to do it that way. As a matter of fact, I think there's a web work problem that asks you to do that, and there are some problems that you're expected to do to be able to do that. So, so let's have a look at this following example. If I get to turn, there we go. For this example here, the manager of a city bus line estimates the demand function to be D of P equals 150,000 times 1.75 minus P square rooted, where P is the fare in dollars. The bus line currently charges a fare of $1.25, and it plans to raise the fare to increase its revenue. Will this strategy succeed? So the first thing I'm going to do is I'm going to change D of P. So I'm going to need to take a derivative of it into 150,000 times 1.75 minus P to the 1/2 power. And I'm also going to need the derivative of P, of D, of the demand function. If I do that using the chain rule and the power rule, I'm going to have 1/2 times 150,000, which is 75,000, times 1.75 minus P, now to the negative 1/2. And now I did the derivative of what's inside the quantity, and the derivative of that, the 1.75 becomes 0. The derivative of negative P is just negative 1. So when I start calculating E of P, I'm going to have negative P times negative 1 times 75,000 times 1.75 minus P to the negative 1/2 all over 150,000 times 1.75 minus P to the 1/2. Now obviously I want to carry some simplifying through this. Since both do have a multiplication of 1.75 minus P to some power, I can carry through exponential rules to take care of that. Negative P times negative 1 is positive P. 75,000 divided by 150,000 is 1/2. 1.75 minus P to the negative 1/2 divided by 1.75 minus P to the positive 1/2 becomes 1.75 minus P to the negative 1 power. So what it would look like, E of P would equal P over 2 times 1.75 minus P. Or you could even say P over 3.50 or 3.5 minus 2P. So this is the function that describes the elasticity of demand. So now I'm going to calculate what that is when the price is $1.25. So I'm going to have 1.25 over 3.5 minus 2 times 1.25. And I get 1.25 over 3.5 minus 2.5, which is 1.25 over 1, which is 1.25. That's greater than 1, so this is elastic. If that means that this market, the demand is elastic, so a price change is going to have an effect on demand. And typically when prices get raised, demand goes down. So with it being elastic, raising the price at this price point will cause your demand to noticeably decrease, and therefore you'll get less riders. So this strategy will not succeed because of that, because if anything's going to happen, his revenue will decrease if he raises the fare. What he really should be doing is lowering the fare to increase the demand and therefore get more riders and therefore get more revenue. So now it's going to be your turn. A Middle Eastern oil producing country estimates that the demand for oil in millions of barrels per day is D of P equals 9.5 E to the negative 0.4 P, where P is the price of a barrel of oil. To raise its revenues, should it raise or lower its price from its current level of $120 per barrel? So let me give you a moment to come up with your calculations, but I am going to ask you this question in 3 phases. The first question I'm going to ask that you answer, first of all, is what is the elasticity of demand at $120 per barrel? Based off this elasticity of demand, is it an elastic, inelastic, or unit elastic? And then to round this out, based off of this information now, should they raise or lower the price? Okay, now that you've answered your 3 parts of this question, to get the final answer, let me go through what I would have calculated for this. So again, we have D of P being given to us as 9.5 E to the negative 0.04 P. That means that D prime of P is going to equal the same thing again. Times the derivative of the exponent, which would just be negative 0.04. So D prime of P is going to equal, if you give me 1 second here, negative 0.38 E times the negative 4P power. So when I calculate E of P, that's going to be negative P times negative 0.38 E to negative 0.04 P over 9.5 E to the negative 0.04 P. When I do some simplification here, I get here that I'm going to have 0.38 P over 9.5, because since they both have a multiplication of E to the negative 0.04 P, these would just cancel out. So, and when I carry through that, I get 0.04 P as being the function that gives me the elasticity of demand for this circumstance. So now I have to see, okay, well, what is that when the elasticity, or when the price is at $120 per barrel? So we have 0.04 times 120, and that's going to equal 4.8, which is greater than 1. That means that it is elastic. Yikes. Which means that basically at this point they should lower the price. If they were to raise the price, the demand would change, I mean drastically, but it would change and it would go down enough that not enough people would buy it. So so here for this information, the oil demand would be elastic and they should lower its prices to raise its revenues. One last one for you to try. Demand for movie tickets to a certain theater depends on the ticket price, P, in dollars. According to the demand function, D of P equals 120 times the square root of 30 minus P. Ticket price is currently set at $10. find the elasticity of demand at the current ticket price, and then find the ticket price which will maximize revenue. So for the first part, I'll ask it in two parts here. First, find the elasticity of demand at the current ticket price. Okay, now as a side question before we get to B, based off of that, should they raise prices, lower prices, or keep prices the same? Now, based off of this, you should know which way the prices need to move now, if they need to move at all. What is the ticket price that will maximize the revenue? So would it be the $10 we currently got, or what would be the best price to have for the tickets to maximize the revenue? Okay, now that you've had a chance to answer these questions, let's kind of walk through it. Again, I'm going to change this function a little bit to be 120 times 30 minus p to the 1/2 power, which means that d prime of p is going to be 60 times this to the negative 1/2 power times -1, because that's what the derivative of 30 minus p is. So I could say this is negative 60 times 30 minus p to the negative 1/2. So when I calculate when I make the function up for the elasticity of demand, I should say, I'm going to have negative p times negative 60 times 30 minus p to the negative 1/2 all over 120 times 30 minus p to the 1/2. When I simplify all of this and put it all together correctly, I end up with the function p over 2 times 30 minus p, which I could also write as p over 60 minus 2p. At a ticket price of $10, I'm going to have 10 over 60 minus 2 times 10. I'm going to have 10 over 40, which equals 1/4, which is less than 1. So basically at this point, the elasticity is inelastic. The demand is inelastic here, which means that raising or lowering the price is not going to have a major effect on this. So chances are, to increase my revenue, I'm going to have to raise the price. So I want to see, okay, well, to answer the question, what ticket price would maximize the revenue? Well, as we said before, for me to maximize the revenue, or to be at a maximum revenue, is when I should have a elasticity equal to 1. So I'm just going to set my elasticity function equal to 1 to see if I can, see what price point would cause that to happen. So I'm going to have multiply both, I'm going to cross multiply. I end up with p equaling 60 minus 2p. I add 3p to both sides. I get 3p equals 60. Dividing by 3, I get p equals 20. So that means that to maximize revenue, the price should be set $20 per ticket. Which, if you're a theater-going person, you probably wouldn't particularly like. But chances are, if this function is correct and the elasticity is calculated correctly, you're going to pay it anyway. So, but that is the answer to these questions. If you have any further questions, please ask about them in class. I will see you then.